So, okay, in the last class we have started the assembly language programming of 8086. So, we have discussed one program. So, the next program is to compute, say y is equal to sigma wi xi, say I varies from 1 to 100, where xi and wi are signed numbers, 8-bit numbers. And assume that there is no overflow. So, to compute y is equal to sigma xi wi, so we have 100 numbers of x, 100 numbers of w, you have to multiply and then add. This is nothing but MAC operation, multiply and accumulate. This type of operation will be used in many of the digital signal processing applications. You can multiply and accumulate. So, before writing the program, as I have told, you have to assume the appropriate memory locations. I am assuming that xi is stored in some locations in the data segment starting with 50,000 H, ending address will be 55,000 H, 5FFF, FH, 64 kilobits of the data segment. I am assuming that this is 55,000 to, if I assume the total 100, so this is 55,063 H. Here x1 is stored and here x100 is stored. Similarly, y1, if you assume that this is x array and here I am storing y array. This is y1, so on up to y100. Let us assume that this is some 56,000. H, and you store the result somewhere in 5700 H y. I am assuming that y is also 8-bit. So, this is the basic assumption. Sorry, this is y, this is w. So, with this assumption, first you have to initiate data segment register with 5000 H. As we know that data segment register will contain the upper 16 bits of starting of that particular segment. We cannot directly take the direct data onto this data segment register or any segment register. You take onto some other register, say AX, comma 5000, and you move this data to data segment. And the number of bytes to be added I will take into CX register, so that I can use loop instruction 0064H. Then you take this effective address. What is the effective address of X array? The starting effective address of the X array, from here to here the offset is 5000, and from here to the W array the offset is 6000. So, I am taking this 5000 offset where the X array is present onto some register, that can be either BX, BP, SI or DI. Similarly, we can take this 6000 into some other register. So, I am taking this BX with 5000. So, LEA. So, we are loading this SI with the offset of W array, which is 6000H. So, let us assume that result is 16 bit, because if you multiply to 8 bit numbers, the minimum result is 16 bit. I am assuming that here result is 16 bit. So, I am storing in 5700 and 5701 Y value. 57,001 I am storing here Y value. Okay. So, I am starting with this is like you have to multiply and then accumulate. So, for the accumulation, initially I will take that accumulator, I will clear that accumulator, and whatever this multiplied value I am going to add to the that accumulated value. Okay. This is something like if I want to multiply 5 onto 6. If I want to add, say for example, what I will do is here x1 w1 plus x2 w2 plus so on up to x100 w100. So, I am taking one register with 0 0 initially. You multiply this x1 w1, you add to this register, and this value will be stored here. After the first iteration, x1 w1 will be stored. Then you multiply x2 w2, you add to this one, so that the sum of these two will be stored again in this register. This I am taking as some register dx. Then again you perform x3 w3 and you add to the contents of the dx. So, that is why I am initiating initially a dx register with 0 0 0 0. Move dx comma 0 0 0 0 h. So, all the partial products I am going to add to the dx. Initially I am clearing the dx. So, after the first iteration I will add x1 w1. So, 0 plus x1 w1 will be x1 w1 itself. In the second iteration, the contents of dx plus x2 w2. The previous contents will be x1 w1, now x2 w2. The sum of these two, this partial product will be stored. After the 100 iterations, this dx contains the total sum that I am going to store in two consecutive locations. Here w and x are 8 bit numbers. So, in order to multiply, I am taking 1 onto some register, 8 bit register. Move AL comma contents of BX. So, what is this instruction? This instruction will take x1 BX is pointed to offset of 5000. With the offset of 5000, what value is there? x1. So, after the execution of this instruction, AL will be loaded with x1. I have to multiply this with w1. Okay. So, w1 is there in location 5600, whose offset from the starting is 6000, which is pointed by SI. So, we know that for 8 bit by 8 bit multiplication, and this is we are assuming that they are signed numbers. So, you have to use IMUL instruction. So for 8 bit by 8 bit multiplication, one of the operand will be by default you have taken to AL. So I have taken this one of the operand into AL, that is why. The second operand you can take into memory or register, any register or memory. And the where the 16-bit result will be stored in AX. This is the operation in multiplication. Okay. So here I am going to multiply I mul byte PTR contents of SI. So what will be operation in this particular instruction? This will multiply AL with, this is memory location. Which memory location? Whose offset is present in SI. Okay. So the memory location whose offset is 6000 is W1. So this will multiply with this AL is having X1 and this memory. Now here we have memory which is W1. Because I want to take only a single byte, I am assuming that W is 8 bit number. So that is why I have written byte PTR. So a question may arise that why you have not mentioned here a byte PTR BX, because the destination register is 8 bit, by default this will take only byte. Okay. Whereas here, so one is AL, the other is SI, means it can take either byte or word. That is why you have to mention byte PTR. So now what will happen? This AX will be having W1 X1. This I have to add to DX and you store this result into DX. Add DX comma AX. So the initial value of DX is 0 0 0 0 and AX is W1 X1. These two will be added and result is stored back into DX. So after this instruction, DX contains 0 0 0 0 plus W1 X1. So this is W1 X1. Okay. So this operation you have to perform 100 times. Okay. So for that, in order to point the next X2, W2, X2 is with offset of 5001, W2 is with offset of 6001. Here we have 5000 and 6000 will be pointed by BX and SI. You increment both the register by 1. INC BX, INC SI. Then because CX is pointed to the array of length, okay, and if I use loop instruction, by default that CX will be decremented by 1. So I can use now loop up, so that Cx will be decremented by 1. If Cx is not equal to 0, it will go to the up. So in the up we have to perform x2 into w2, we have to add to w1 x1. So where should be this up? This up will be now in here. Now what will be taken into AL? In the second iteration, the contents of the location whose offset is present in BX. So what is the offset in BX? BX was initially 5000, here I have incremented by 1, so that this will be 5001. So the 5001 contents will be 55000, means 5001 is offset x2. So here x2 will be taken into AL in the second iteration, and here IMUL byte PTR SI. Okay. SI was 6000, after one increment 6001, the offset with 6001 will be W2 value. So W2 and W1 will be multiplied, and here in AX what will be there? W2 X2. This I am adding to DX. What was the D in DX? W1 X1. So now after this, DX contains, the earlier contents are W1 X1, now we are adding W2 X2. So this will be W1 X1 plus W2 X2. Again we will increment Bx so that it will point to X3, we will increment Si, it will point to W3 because the 100 multiplications are not over. So, Cx will be decremented by 1. So, again it will go to the loop. So, when does this will come out of the loop? After multiplying all the 100 numbers. Okay. Once it is coming out of the loop, where this result is there in dx. Okay. We have to store this dx onto the register this. So, for that you can write LEA BP, you have base pointer with a, what is the offset where we have to store the result? From here to here, the offset is 7000. So, I am pointing this to 7000. Then store the result, where the result is there, y 16-bit result is in dx. Okay. So, move word ptr bp comma dx. So, the result 16-bit result of y was there in dx, that I am moving to two locations because word ptr. So, BP has pointed to 7000, but the result is 16-bit. So, this will store in 57,000 and 57,001. Then halt. This is the program which computes y is equal to sigma xi wi. So, this is an important operation in DSP. This is multiply and accumulate operation. Okay. If you take the filter, same operation. If you take the transform, also we have similar type of operations. This is the second program, and I will take a third program on multi-byte BCD addition. See. Means if I want to add, if I take 2 bytes 3259 decimal plus 4928 decimal. I want to add this. Let us assume that there is no result, is also only 16-bit, there is no overflow. So, what is the expected result? 17, 8, 11, 8. So, you can extend this to any number of bytes. Okay. So, I am taking for the sake of simplicity only 2 byte. Multi-byte means you can have any number of the bytes. So, this is the BCD addition I want to perform. Okay. So, for that you assume the appropriate memory locations. Same data segment. Say starting address is same 50,000 H, ending address will be, if it is 64 kilobytes, 5FF FFH. So, to store this first number we require 2 locations. Okay. So, I am taking this location with the offset of say 1000. So, what will be the address? 51,000 H. H. Here I am storing the first number. This is 4 digit, which is 2 byte. So, I require 2 locations. Okay. So, even if you store these decimal numbers, the microprocessor will assume that it is a hexadecimal number. So, you have to do some manipulation to get the decimal result. Okay. And then I am storing this second BCD number, which is 4 digit BCD number or 2 byte number with the offset of say 5200. Here I am storing second 4 digit or 2 byte BCD number. If I take this example, this can be any data. If I take this example, so this 59 will be here, 32 will be here, 28 will be here, and 49 will be here. So, for the sake of simplicity, what I will do is, I want to store the result back into this location. Okay. After the execution of this one, I want to store this 87 here and 81 here. After the execution, I want to replace this 28 with 87 and this 49 with 81 for the sake of simplicity. Okay. Now, what will be the program? We have 2 byte addition. So, initially we will move that this common instructions will be there. So, data segment will be 5000, move AX comma 5000H, then move on to data segment register. Then you point this where the first term in 4 digit BCD number is there, starting off that one, that offset into some register. This is same as the previous programs. Okay. So, I am using again BX and SI, and because I have to add 2 bytes, we can store 2 onto some register, move BX comma 1000 H, move SI comma 2000 H, move CX, so that I can use the loop instruction. How many byte addition you have to perform? Is 2 byte addition. So, you can take 0002H. Then first you have to add. Now, the question may arise that why do not you perform directly 16 bit addition? Because the microprocessor 8086 is 16 bit microprocessor and we have 16 bit registers, we can add 16 bit together. The reason for that one is, here this is BCD addition. So, in order to get the BCD result back, okay, so this will operate only on register AL only. Okay. For example, if I add this 59 and 28, the microprocessor will take this one as hexadecimal. The actual decimal result will be 87, but this will comes to 9 plus 8 is 17. 17 is nothing but 15 is F, 10 will be 16, 11 will be 17. This will be 81H in hexadecimal addition, but we want 87. To get 87 decimal from 81H, 87 decimal, we have discussed the instruction. So, which instruction will be used? There is an instruction called DAA. So, this DAA instruction operates only on AL only, this is only 8 bit data only. That is the reason why I am performing this 2 byte addition. If this is hexadecimal, I can perform 16 bit addition in a single step, okay, because this is decimal BCD. So, I am taking this as 2 bytes because I have to manipulate the data in AL only. So, this DAA register will operate with only 8 bit data which is stored in AL. I think the justification is clear. Then what you have to do? In order to perform this addition, one of the operand has to be taken into AL. So, move AL comma BX. So with this instruction what happens? Here no need to write the byte PTR because the destination is 8 bit. So this AL will be stored with the contents of the memory location whose offset is present in BX. So BX is pointed to 1000 with the offset of 1000 59. So AL will be loaded with 59 value. So even we have given this one as a decimal, but the microprocessor assumes that is hexadecimal number. Okay. Now we have to add to the previous one. Add along with carry. Of course here there is no carry, carry is 0. After this addition you may get carry from here to here. Okay. So for that what you have to do is you write an instruction to clear the carry, CLC, we have discussed in the earlier class. This will clear the carry flag. So even if I add ADC here, because the carry flag was reset and this none of these move instructions it will affect the carry flag. So carry flag is 0. So this two data ADC AL comma contents of SI. So what is the operation here? The contents of AL will be added with contents of SI plus carry flag status. These three will be added and result is stored in AL. The operation inside this ADC AL comma contents of SI is contents of SI, which is contents of SI is 2000, in a 2000 offset 28 is there. So this with this instruction this AL is having 59, this will be 28, and because I have cleared this carry flag this is 0. Okay. So these three will be added and result will be stored in AL. So what will be there in AL? This will be 81 because this will assume hexadecimal, but the correct actual decimal result is 87. So to get that, after this you have to write DAA, so that in AL you will get 87. Okay. Then we have to decrement CX until the CX is equal to only 2 bytes. If I want 4 bytes, you just simply load this with 4. Okay. So this can be extended to any number of bytes. So the next instruction you have to decrement CX, but if I use the loop instruction, inherently CX decrement is present. So I will write, so because the second byte is pointed in 1001 and 2001. So before writing the loop instruction I have to store the result also. So where I want to store the result, I want to replace the second number with result. Where the result is present now, after this in AA, AL, the result 8 bit result 87 is present. That I want to store back with the offset of 2000, which is pointed by SI. So the instruction will be move contents of SI comma AL, so that this 28 will be replaced with the lower order result 87. Okay. Now INC BX INC SI loop up. Where should be this up now? It should be here. So that after this INX BX, now AL is loaded with 32 and contents of SI becomes 49. So these two will be added, result is stored in AL, which will be, so if I add this 81H, this 32 plus 49, this will be A7. So after the second iteration, the contents of AL will be 7A because this will perform hexadecimal addition. If I write DAA, then this 7A will be converted into 81. 81 will be stored, and that 81 I want to store back into the destination register. where this second 4-bit BCD number is present. So, I will write move SI comma AL. So, this 81 will be replaced by 49. Then INX, BX, INX, SI, because in the first iteration CX was reduced to 1, now after the second addition CX will become 0, this will come out of the loop. Okay. That is the task and you have to halt. So, this is about the multi-byte BCD addition. So, this program can be extended to any number of the bytes. If you have 5 bytes, simply load this with 5. Okay. If you have 10 bytes, simply load with A. Okay. So, like that you can extend to any number of bytes. This is about the third program, which is multi-byte BCD addition. Okay. So, if it is multi-byte binary addition, we have performed without using this loop and all, we can perform in a single stage. Okay. The third example is, I will use some program on ASCII. Again say multi-byte ASCII addition. Here I will assume that the same 2 ASCII digits are there. So, I have to add 2 ASCII digits, then you have to store result in ASCII. For example, if I take this 32, 39 plus 38, 34. This is ASCII code corresponding to 29. This is ASCII corresponding to 84. So, as I already discussed while discussing about this ASCII instructions. So, 0 is nothing but 30 H. If I press the 0 key, if it is ASCII keyboard, internally 30 H will be generated. Simply how to add 30 to that key. 1 means 31, 2 means 32, so on up to 9 means 39. Okay. So, this is actual addition will be 29 plus 84, 29 plus 84. So, this should be 13, 11. So, 1 is carry flag. So, the correct expected result will be 13 ASCII. Okay. If I perform this, if I give this data to this microprocessor, this will assume that these are hexadecimal numbers, and what result you will get? This 9 plus 4 is 10, 13, 13 is nothing but D 6, A 6, you will get 6A 6D, but I want the result as 13. Okay. So, for that what is the procedure? Again you assume that the same memory locations, this in 2 consecutive locations with some offset, the second ASCII digit in 2 more consecutive locations, and you store back the result in the second number. You just replace the second number with result, similar to the previous program. Okay. So, let us assume the same locations. Data segment, H. With offset of 1000, this is 51,000. Here say 39 is stored, and 50,001, 51,001, say 32 is stored, and 52,000, 34 is stored, 52,001, 38 is stored. This is ASCII correspond to 9, ASCII correspond to 2, ASCII correspond to 4, ASCII correspond to 8, and you store the result back onto this. Okay. So, what is the ASCII correspond to this 1? This is decimal result. So, ASCII will be, the result of ASCII will be this is hexadecimal result. What is the correct ASCII result? This is 9 plus 4, 9 plus 4 is 13. So, this will be 1 is carry flag will be set. So, this will be 3, means 33. This is 8 plus 2 is 10. Okay. So, which is 1 0, carry flag will be set, 0 means 30. So, this is the result, correct result that I want to store. This is the ASCII correspond to 0. This is the ASCII correspond to 3. In this case, we are getting the carries. Okay. So, this result I am going to store back this here. This 33 I want to store here, 30 I want to replace with 38. Okay. So, what will be the program? So, move AX comma 5000. These are common in all the programs till now I have discussed. Move ds comma AX, then move bx comma 1000, move si comma 2000, and each contains, we have to perform again the same logic here also. You have to perform this addition first, then this addition, because the instruction I am going to use here will be AAA, ASCII adjust after addition. Okay. So, here also you have to operate, this will operate only on AL. So, I have to use 2 byte additions. So, I have to perform this in 2 iterations. So, I am going to take this 2 onto CX, so that I can use loop instruction. Move AL comma contents of BX. So, I am taking the, so this 32, 39, 38, 34. So, BX was 39, 39 will come into AL initially. Then add along with carry, here also you have to clear the carry flag. So, that in the first addition there is no carry, during this you may get the carry, that you have to add here. ADC AL comma contents of SI. Then you have to write AAA. As I have told, after this what will be the contents of this AL register? This will be D6. So, if I write this AAA instruction, what is the correct this ASCII? 9 plus 4 is in fact 13, 1 is carry flag. So, these 3 ASCII character will be 33. So, I want to store 33 into destination register, but after ASCII what happens is this will give unpacked BCD result. So, you can refer to this AAA instruction. So, AAA instruction basically stores the result in unpacked BCD form, it is not direct ASCII. Okay. So, this only this 03 will be stored after this. ASCII will, I will repeat that again, that AA instruction. So, in AA instruction, if I add 2 ASCII numbers, say 32 plus, I am taking here example without carry, so that it will be clear, say 35. Okay. So, if I want to add these two, move AL comma 32, move BL comma 35, add AL comma BL. So that what will be there in AL here? 67. If I write instruction AAA, so what is correct? This is ASCII correspond to 2. This is ASCII correspond to 5. So 7. ASCII of this one is 7. So after this what happens is AL will be containing 07, which is unpacked BCD. This is called unpacked BCD. Okay. So this AA instruction adjust AL contents to unpacked BCD, but it will not give the ASCII. If you want to get ASCII back, what you have to do is, so this is 7 ASCII. What is the code? ASCII code correspond to 7 is 37. But here after this AAA, this will contain only 07. To get 37 back, we can add 30 or you can OR with 30H. Or AL comma 30H, or you can simply add also. So that after this what will be the contents? AL will have 37H. 0 if OR with 3, you will get 3 itself. 0 if you OR with 7, you will get 7. Or instead of this you can write add AL comma 30H. You can write any one of these equations, these instructions. Now here coming back to this main program, after this addition what happens is this 39 plus 34 which is 6D, but actual this one is 9 plus 4 is 13. So this 03 will be there in AL. But what is ASCII code correspond to 03 is 33. So you have to either add or you have to OR. OR AL comma 30H, so that AL will be having 33H, which is the ASCII correspond to 3. This I have to store back into, I have to replace the second number with this result. So you have to store means move contents of SI comma AL, so that this 33 will be saved back into, it will replace this second number 34 with 33. Okay. Now the first byte addition is over, you have to go for the second byte addition. Before going for the second byte addition, you have to increment the contents of BX SI and you have to decrement CX. That is not required if I use a loop instruction. So INC BX INC SI loop up. So this, where should be this up now? This up should be here. So that the second data 32 will be taken in AL, 38 will be pointed by SI because we have incremented SI, these two will be added. So the result will be this 32 places 6A, 6A will be there here in AL, and if I use ASCII, before ASCII 6A will be there. So after ASCII this AL will be containing unpacked BCD, BCD of this one is 00, because 8 plus 2 is 10, 1 is carry, so the result is only 0, AL will be having 00. So to get 30, which is the ASCII code correspond to 000, so you have to OR with 30H, then the result is stored back into the second number, then only halt. This is the program for ASCII addition. So mainly these two programs will demonstrate the functions of DAA and AAA. So these two are the two important instructions, because a layman understands only the decimal digits. So that is why he will expect the result also in decimal. Similarly, keyboard is actually ASCII, but if I press this key, any key, the corresponding ASCII code will be generated. Okay. So now to convert back that ASCII code into decimal also, we can stop here without adding the ORing with this 30H. And if I want ASCII only, if I want further processing of the ASCII digits, I can OR with 30H. Okay. This is the fourth program. Then I will discuss another program, say compare 50 decimal bytes or words, say. So, and you stop whenever a match is found or end of the array is reached. Okay, this is the next program. So, I will explain what is this. Here I will use two different segments. This is data segment, this is extra segment. As I have discussed in the earlier classes, whenever the data is in excess of 64 kilobytes, you can store in extra segment. So, the starting address is say some 50,000 H, 64 kilobytes, 5FF, FFH. So, the next address itself is 60,000 H is the extra segment, and this is 6FFFFH, and you take some offset here, the offset of some 1000, and you take here offset of some 2000. You compare 50 words, nothing but 100 bytes, okay, but I am comparing as a whole word itself, okay. This is word 0. This is word 49. Totally I want to compare. This is word 0. This is word 49. Totally I want to compare 50 words. You take the 16-bit data, you compare with the 16-bit data. Similarly, you go for the next 16-bit data, you compare with this. Like that, you goes on comparing this 16-bit words with source and destination. So, how to stop when? So, whenever the end of the array is reached, this will be 51063H, and this one will be 62063H. So, how to end after comparing all the 50 words, or we can end in between if there is a match, if these contents are same. For example, if you have something like 3E3F, this is also 3E3F. After the first comparison itself, you have to stop. Otherwise, if these two are, the 16-bit word is different, then you have to go for the next comparison. Okay. So, we have to stop at a point where both the words are matching is one condition, and second condition is if the end of the array is reached. Okay. Now, here this is slightly somewhat different because I am using two different segments. So, the program will be move AX comma 5000, this is data segment register, and this is extra segment register is 6000. Move DS comma AX, again you will take move AX comma 6000, move ES comma AX. So, that I am initiating this data segment and extra segment with 5000, 6000 respectively. Then the offset, load effective address. So, in string operations we know that this will be source index, this is destination index. SI with the offset of this one is 1000, and load data segment with offset of 2000, and total 50 words you have to transfer. So, move CX comma 50. What is the hexadecimal of 50? 50 is 16, 3 are 48, 2, 16, 0 ja 3, 0 0 32H. 64 will be 100 bytes, 32 hexadecimal is equivalent to 50 decimal. Okay. Now we can directly write compare string word. So inside this instruction it will compare the source and destination, okay, but it will compare for 100 iterations, 50 iterations. If I add a prefix called repeat not equal, if there is no match, then only it will go here, is one condition. Without this, until the end of this one, once the end of the array is reached, it will come out of this loop. If I add this prefix also, whenever the match is also there, it will come out of the loop. Okay. Without this, after the end of the array only it will come out of the loop. If I add this prefix, whenever match is there also, it will come out of the loop. Okay. Loop up. Where should we sub? Sorry, here there is no loop because this is inside this itself is there. So only simply halt. Because this compares SW, this repeat will act as loop. Okay. So this is the program to transfer, to compare 100 bytes, and it will stop whenever the end of the array is reached, or otherwise if there is a match. Okay. So I will discuss some more programs in the next class. Thank you.